Hello and welcome to today's webinar, which is being presented by Cutting Tool Engineering and the RobbJack Corporation. I'm Dennis Spaeth, the owner and publisher of Cutting Tool Engineering, and I'll be serving as your moderator today. It's my pleasure to introduce our presenter, Mike MacArthur, Vice President of Engineering for the RobbJack Corporation, which is in Lincoln, California. Mike has worked for RobbJack for over 25 years. He began as a tool grinder and has just about held every position available, including an extended period as an applications engineer. Today, as Vice President of Engineering, Mike leads RobbJack's research and development efforts, as well as technical sales and customer support. He is actively involved in developing new tools and processes for the medical industry. With that, I'm going to flip things over to Mike.
Good morning, everyone. Afternoon for some of you. Once again, this is Mike MacArthur from RobbJack Corporation, and some of the main goals that we're going to try to do today is talk about tips and tricks and new tools and how to make it easier to machine medical parts and tool holding and tolerances for consistency, new CAD/CAM procedures and programming techniques that help problem solve and improve your processes, new cutting tools to solve problems, new software to find accurate cutting data, which is usually a big problem for people to find accurate cutting data, and how you can apply all those together to get about a 500% improvement. And then we'll go over the questions at the end. So when we talk about tolerances in the medical field, you guys are dealing with very tight tolerances and micron type tolerances. But a lot of people don't realize how tight some of the tolerances that we're holding on the cutting tools that we grind for you. So as an example here, you could see this is a leg on an ant, and this is a hair on the ant's leg. So that's about 1/10, 20 millionths diameter. Some of the tolerances that we're holding are sub-micron level, and on the roundness and things like that on the cutting tool. And so the tolerance that we're holding is about 5 times smaller than the hair on that ant's leg. As well as like a human hair, the tolerances that we're holding are about 120 times smaller. So it's very, very tight tolerances and precision type of geometries that we're talking about on these cutting tools. The big thing that's kind of the foundation and is often overlooked is that tool holder to shank connection. A lot of people tout H6 tolerance to be very, very tight tolerance work. We hold every tool to H4 tolerance. And what that does is not only on the gripping force and keeps tools from pulling out of the holder and inaccuracies of that, but it's about 5 times tighter tolerance than some of the other, like even up to H6 tolerance, it can be 5 times tighter. So what that does is it gives you an increase in accuracy and repeatability, which is paramount in the medical field. What that relates to as far as like diameter, it's a minus 50 millionths of an inch tolerance to a tenth and a minus a tenth and a half. So very, very tight tolerances on tools 3/8 of an inch and under, and still very tight, a 1/10,000th of an inch total tolerance on tools over 3/8 of an inch. What does that relate to? It gives you about 10 to 30% more gripping force for every 10,000th of an inch that we're closer to nominal. The other thing is a lot of tools will have polished shanks. So this shank that you're trying to hold on to is very polished. It looks nice, but you really don't want a polished shank on something that you want to hold, and you don't want it to slip in the holder. And so by having those super tight tolerances on the tool, it reduces the TIR and run out of the tool, so the cutting edges are a lot more accurate. These 3 types of taper on a tool are obviously exaggerated in these images, but they're very common. This barrel shape, the concave shape, and all of those things reduce the accuracy in the holder and reduce the gripping force that you get in the holder. So by holding tight tolerances, we can help make it a much more repeatable process that improves your performance. I kind of wanted, since you can't be here with us, I kind of wanted to give you a little quick tour of RobbJack. So here's like a minute video or less, and it kind of shows some parts of our facility. So RobbJack, kind of a really quick background. RobbJack is all made in the USA. Here's our team right here. And what's unique about us is we're an ESOP company. So all the employees are owners of the company. It's kind of unique, but it allows us to have more pride in what everyone's doing because everyone's an owner. And then RobbJack did add a huge solar 1 megawatt generation facility to try to generate as much electricity as we're using. So there's a big 3-acre farm behind RobbJack, as well as all the around the building. We have the solar panels as well. So going into the machining part of things, we're going to talk about new CAD/CAM processes and things to improve performance when you're machining the difficult medical materials like titanium, stainless steel, cobalt-chrome, the hard metals for molds and forging dies, those types of things used in the medical industry. The thing that you really want to concentrate when we're talking about this new type of programming and things like that is this one piece of information right here. You want to use tools that are about 50% of the size of the tightest area or the slot that you need to produce. You really want to get that tool to be about 50%. So if this was a 1-inch wide slot, you would want that tool to be 1/2 inch. And what that does is allows you to have the movement that you need as the tool goes around to minimize the angle of engagement. And we'll show some slides and things like that, what we're talking about. But essentially, you want to minimize the surface contact. It helps reduce heat and things like that. Now, this type of technology that we're going to talk about on the CAD/CAM side and programming it's great for miniature tools. It's great for large tools. One medical example would be like Torx bone screws and doing that hexalobular shape. That's an excellent example of a medical application for this type of programming. So here's a video. This is a very hard part, 54 Rockwell hardened part, and we'll show you what this type of tool path does, and note the temperature at the end of the video. And Dennis, if you wanted, I think I forgot to say you could do one of the polls now if you wanted to do
Sure.
the poll. Yeah.
Okay, this would be what is your biggest pain when machining? So what you'll see on your screens right now is just a quick poll. I'll leave it up there for a couple of minutes. Just select one of the following options for whatever is your biggest pain when machining: tool breakage, slow cycle times, getting accurate speeds and feeds, finding the best tool or poor finishes or part quality. Once you've done that, just hit the submit button. And again, I'll give it about 20 more seconds or so, and then I'll.
While we're doing that, we'll watch this video. And cutting very difficult material, that tool is about 50% of the slot width. And we're cutting 54 Rockwell material at 125 inches per minute, very fast feed rate. But the biggest thing to do is to look at the temperature when we're done cutting this material. And this works really well for titanium, for cobalt-chrome, nickel alloys, all those difficult to machine materials. When you do this type of light radial cut, the temperature of the tool was 72 degrees, the part was 70 degrees. And we were able to do that with the technique of that tool path. So here's an example of a tool path. At the beginning, when CAD/CAM systems first came out with the Trochoidal tool path, it was really only good for like what you saw, a slot, because there was a lot of wasted movement. Now they're all very hybrid type methods of doing this. So it analyzes it and it only does a Trochoidal cut when it needs to. And then it can do like traditional types of cuts when it's not in that area. So you don't have any of that wasted air movement. But most of the CAD/CAM systems have this. As an example, like Mastercam, they just call it different things. Mastercam calls it dynamic milling. Autodesk calls it Fusion 360, or Fusion 360 is the CAD/CAM system. Adaptive clearing. Esprit calls it profit milling. Surfware calls it true mill. Volume mill, that's kind of one of the pass and volume mill. They all have it. They just call it different things. But if you can do that high efficiency machining, and we're going to refer back to that quite a few times in this presentation because of all the benefits it has with extending your tool life, getting faster feed rates, things like that. So why does that benefit? Why is it so beneficial? And this is kind of the secret sauce of what it does. Is here's an example of doing a full slot, a heavy profile, and you can see this red section here. That's the piece of the pie that's engaged in the cutter. And so what this does is, as this tool comes around and is rotating, when you're in a light radial with a cut, the tool spends a lot less time in the cut and a lot less time generating heat. So it's in that cut for a very short period of time. So this is kind of the recommended 10% with a cut or 37 degrees angle of engagement for most of the difficult materials that you're going to encounter in making medical parts. And when you do this type of thing, it reduces the heat generation. So here's an example of the full slot versus the light radial with a cut. What happens in very difficult materials like titanium and stainlesses and cobalt-chrome is if you try to do that full slot, you either have to go very conservative speeds and feeds and very slow type of process, or you get what's called a heat accumulation. So that flute heats up, it has a little bit of time to cool down, it heats up, but it's heating up more than it's cooling off in the time that it's out of the cut. So what you have is you get past the fatal temperature of the carbide or the coating or the material that you're using on the cutting tool, and what happens is you chip up the tool, it generates more heat, and it actually will skyrocket straight up. So what this continuous cooling action does when you go a very light radial with a cut is you heat up and you're shedding about the same amount of temperature as you're heating up on the tool. So we're very far away from that fatal temperature of the coating. So what doing this is allows you to go much higher surface footages. So you're able to go much higher surface footage, like a normal surface footage cutting titanium may recommend 150 surface feet. 230 surface footage. We're recommending 400 because we're able to cut and use this continuous cooling action. So here's two examples. And Dennis, if you want to do that second poll, you can do that now.
Okay. So I'm doing what is the most common material that you're machining? So Mike, and I think that before we continue on, let's give everyone about a minute or so to respond to this poll.
Perfect.
What is the most common material you are machining? Stainless steel, cobalt, chrome, titanium, PEEK or other plastics, or aluminum? And just hit the submit button when you're done. And again, I'll give this about another 25 seconds. And I think we've got just about everybody. So I'm going to go ahead and close the poll and throw it over back to you, Mike.
Perfect. And we're going to go over those poll results at the end. So if people had issues, major issues with, like on the first poll, tools breaking, we'll try to address those things and help you out. But here's two examples of when using the new high efficiency tool pass, what we're able to achieve. Much faster speeds and feeds. We're cutting stainless at 100 inches per minute and titanium at 75 inches per minute. And we're able to do that very repeatedly. We don't have issues. We get the same amount of tool life, and we're able to get through parts much faster and get a lot more throughput out of these tools than you would doing it the more traditional ways. And what we do is we have specific geometries that take advantage of this new high efficiency tool pass and things like that. So in this example, in the 304 type of stainless or other types of stainless, we're taking a 3/8 diameter tool at that 10% width of cut, and we're running it 2 times the diameter depth of cut in a single pass. So 3/4 of an inch deep and 37 thousandths wide. And we're able to cut at 100 inches per minute, and it sounds beautiful. It's not squealing, it's not squawking. It's a very beautiful sound as you're machining. And we're going to show a titanium part in just a minute. Same thing this is with a 1/2 inch tool going 10% step over, which is 50 thousandths, but 1 inch deep in a single pass. So here's a video of a part done that way. So the tool's not struggling. It's cutting very freely. The chips look really nice, and we get really consistent results. And this part's a lot bigger than your traditional medical type of part, but the amount of cubic inch removal rates and the amount of chips that we're able to remove is pretty staggering. I'll show you as soon as this video is over the pile of chips that we produced in 1 hour, which is not even the tool life of the tool. It's able to machine a lot of material doing this type of cutting. So here's a pile of chips made with one tool in an hour. And the tool lasts a lot longer than that hour, but we couldn't pile up any more chips without it falling off. So that's the amount of chips that one tool's producing in an hour. Here's a medical part example of like a bone screw. We talked about that Torx or hexalobular shape. And in this example, we were able to get a 550% reduced cycle time by utilizing that new technology, by using specialized geometries that that were designed for that type of cutting. We were able to increase the strength of the tool, and we were able to use specialized coatings. All that together, as well as with the programming, we were able to reduce the cycle time by 550%. Some of the other things that we developed that really sped things up is we came up with tools that just plunge all those shapes and form tools all in one pass, and like this example in the middle. And then we developed flat bottom drills that were able to rough out material and produce flat floors, but able to plunge it instead of doing all that machining. So those things together were able to get pretty significant cycle time reductions. And then we also have the slitting saws that we're going to talk about more later that can do the threads and things like that. Another medical part kind of example would be like spinal implants. I believe this one is a carbon filled PEEK, so it's very abrasive, but a lot of people are, you know, doing more traditional PEEK type of parts for making like spinal implants, and using PEEK because it's you're able to x-ray it and able to see through the x-ray through the implant to see the underlying tissues and things like that. So they're used in a lot of implants, PEEK, carbon filled PEEK. But the big issue with machining those materials is they like extremely sharp cutting edges. So we've developed specialized geometries specifically for these types of medical plastics and PEEK materials and things like that to get super sharp cutting edges. Then the PCD cutters that we make are extremely sharp cutting edges. People, you know, they'll drill, they'll sometimes have holes in these parts, things like that. We have specialized geometry made out of solid pieces of PCD in there. So all the cutting edges are PCD, but new technology has allowed us, instead of the old days of having just a flat sheet of diamond on there that kind of slapped off the material, we're able to have all that full rake and relief and angles that you would have on a solid carbide tool on diamond. So we're able to, you know, get better finishes, sharper edges, things like that for the medical parts, and able to really improve performance, speeds and feeds, and get the life with PCD in those types of applications. If you're not using the carbon filled PEEK, a lot of people just use really sharp carbide. Some people will, you know, on the carbon filled PEEK will sometimes use diamond coated inserts and things like that, but everything needs to be very sharp, and you want to be very careful not to heat up the material. You can cause cracks and things to form if you're heating up the material. Slotting, even though you can slot right through the material, a lot of times it's not recommended because you may generate excessive heat. So you may want to use a smaller diameter tool and trochoidal cut those types of things, not because the material is so difficult to cut, but because it's sensitive to those heat issues. Sorry, on the carbide side, you can see all these polished edges. So we polish the cutting edges, we polish the flutes, we have super sharp cutting edges and geometry designed for these medical plastics and things like that. Some of the other medical parts would be like a knee joint and things like that. Where on the knee, you have a combination of materials. You have the UHMW or medical plastics that's used to add that shock absorption and smooth movement and things like that your cartilage would normally do. Then you have stainless steel, cobalt-chrome, titanium, various types of solutions in the metal side of things like that. So on the stainless steel, cobalt-chrome, we have the multi-fluted tools like this tool here, utilizing those speeds and feeds and programming techniques, you can really get increased performance and faster feed rates and things like that. But the more sensitive one is, it seems it cuts very easy, but these medical plastics are ultra sensitive to any kind of mark on the cutting edge. You'll look at this tool underneath a microscope. This wouldn't be a tool for the plastic. This would be a tool for the metals. But if you looked at the tool for the plastics underneath the microscope and you're looking at this cutting edge, even underneath a microscope, it looks like flawless, but you'll get micro scratches and mismatching and things like that on these UHMW or medical plastic parts, because they're so sensitive to any kind of mark on the tool. So we've developed a process that we polish with ultra fine grit diamond wheels and things like that to give it unbelievable finishes on the cutting edges, and that really improves performance and improves the part quality as well. The other thing is on these parts, we'll a lot of times do form tools. So instead of having to do the 3D machining or the complex shapes that are in here, we'll do it with form tools, so you don't have to do all that surfacing. The form tool is producing that type of geometry and really reduces the cycle time when you do that. Here's an example of like a hip joint, and on the hip joint we have a couple things. We have the machining of the hip joint, but then you also have the forging that goes on and the forging dies. So it kind of encompasses a lot of types of operations and things like that, that use slitting saws, that use end mills, that use all kinds of different configurations. So we've developed material specific geometries depending on what that hip joint is made out of. This one is a titanium one, and I want to show you this video because it's kind of unique and novel in that we're using supercritical CO2 for the cooling and lubrication because of they don't want contaminants and things like that, and environmental reasons and things like that. So we developed a saw and Arbor, working with Fusion Coolant Systems to come up with a solution. And so when you look at this video, note that's CO2 coming out, supercritical CO2 coming out as we're machining it, the saw, and that coolant is hitting the saw on both sides. So that is not like a flood coolant or anything like that. That's using CO2. So there's no cleaning of the part that you need to do after. There's no contamination to the part, and yet we're able to cool it and lubricate the saw, and that's a titanium part right there. And so that's the stem of a hip joint. So when they put it in the bone, the bone is able to grow around those slots that we're putting in there. So it's kind of a unique solution that we think is probably going to be taken advantage more, that since this was just developed very, very recently. So I think you're going to see more and more of that type of solution. You know, then we have like the Thru coolant saw solution that we're going to talk about more, where we have able to get ports on both sides of the saw. If you gang them or just one saw, you're able to do that. That's pretty dramatic improvements on performance and quality, because getting the coolant on both sides of the saw equally has always been a challenge with external type of coolant sources. On the forging dies, you know, we have specialized tools for hard metal and things like that for doing the 3D molds or forging dies. And one of the tips and tricks that you want to do is when you're cutting with the saws, you kind of want to arc into the cuts. that really helps performance. So for this application, we're able to reduce the cycle time by about 385%. That was with a flood coolant application. For the slitting saws, like we said, it's a challenge to get that coolant on both sides of the saw. So what we have is we have an arbor with a through coolant and then a channel. And then if you were just using one saw, you would use two of these flanges. So you would have one on the right side of the saw, one on the left, and the coolant would come off on both sides. But if you're ganging multiple saws together, we have these through coolant spacers that puts coolant on both sides of it. So you're able to have coolant on the left side, right side, and it's pretty dramatic performance. We're seeing people reducing their cycle times, 200% is not out of place. It depends on the application, depends on the material, but you get really, really good coolant flow, and it solves a major problem when using slitting saws. And in the medical industry, you use a lot of slitting saws for various applications. On the slitting saw side, most people aren't aware that from 2 thousandths thick to 250 thousandths thick, those are all standard for every 10,000th of an inch in between. So as an example, a 37 thousandths and 9/10ths or 42 thousandths and 2/10ths, those are all standard off the shelf saws. We were able to thin them to whatever thickness you need very, very quickly. And those are all standard saws. Most people look in the catalog, you can't list every 10,000th of an inch. So they see the 30 or 40 saw thicknesses. Those are just the price points where the price changes. So you can get anything in between as a standard. So some people I see fight, thicknesses and things because they think they have to get a certain thickness that's available. Well, every thickness from 2 thousandths to 250 is readily available off the shelf. Then one of the main problems when using slitting saws is overcome. I would say about 90% of all the saw problems you run into can be solved by using our K series. Using the K series saw, it can really improve performance and really eliminate the majority of the problems that you run into when using slitting saws. And like I said, slitting saws are used commonly in the medical industry. When using the slitting saw, if you're cutting a 50 thousandths wide slot, the chip being produced is 50 thousandths thick, and the saw is 50 thousandths thick, and everything's being packed into that little tiny little area. So what we can do is we can put this alternate tooth chamfer on there. If you can see the little chamfer on the teeth, so it's a staggered tooth. So instead of a 50 thousandths slot chip in a 50 thousandths wide slot, now you're only producing a 30 thousandths wide chip, and so there's a lot more room to get the coolant in there, the chip evacuate out of the cut. And then we put twice the amount of clearance on the side, so the saw is getting thinner as you go towards the ID, and we were able to put twice as much on there because we also put a flat and parallel hub. So this flat and parallel hub that I'm going to show you just in a second in better detail is the same thickness as the tooth thickness. And so it solves, slippage problems, chip packing, it reduces the torque. And anytime you're using a saw that's going about 5 times its thickness and depth, or even in like 3 times its thickness and depth, it's a huge advantage by using the new technology. And a lot of people aren't aware, this is the standard type of saw, and it's hard to see, so we blew it up a little bit, but this line is representing the tooth thickness. So it's getting thinner as you go towards the ID of the saw. So it's hard to see, but you're really only making contact where that yellow arrow is, and you're making only contact on the outer ring. So that saw could have a tendency to kick at an angle, have run out, side run out, and things like that. And you're making very little contact on that arbor. When you have a flat and parallel hub, this is the same thickness as the tooth thickness, yet we have a lot more concavity and clearance on here, and we're making surface contact all the way on this surface. So it increases surface contact, it's less run out, increased accuracies, you don't have saws slipping, and whenever you gang more than one saw together with spacers, this hub is a necessity. You really shouldn't ever use a saw like this when you're ganging saws. Now on the aluminum side, I debated to put this in here, but then, you know, talking to some of our customers, I found that, you know, that there's a lot of medical devices that are used, made out of aluminum, as well as components and things like that that are related to the medical field. So they are doing a lot of more aluminum machining than I thought. But we developed tools that really can get rid of all the chatter and vibration when using aluminum to cut parts. And in the medical applications, finish is really critical, and sometimes the length of cuts are longer than normal. So this mirror edge geometry that we developed makes the chip passing frequency and the part frequency the same. So we can get rid of all the vibration by going max RPM. We don't have to slow things down. And in this video, you're going to see a tool going 5 times the diameter and depth of cut in a single pass, which we increased. It was 900% faster than their current operation. So here's a video to show that. So that's the finish that was produced. So I'll pause that to talk about it. So that was going 14,000 RPM with a 3/8 tool sticking out almost 2 inches deep. If you try to take a normal tool 3/8 diameter in aluminum, you know, cutting at 14,000 RPM, 236 inches per minute, it would normally just squawk and squeal, and you would have the worst finish. Tons of chatter, vibration. You'd probably snap off the tools. But as you listen to this, if you can hear it, it's very, very consistent. No chatter, no vibration, and we're able to get that with this mirror edge geometry that we're able to put on there. So if you have an application that you're cutting aluminum and you're running into vibration and chatter, that mirror edge is a magic bullet. It'll solve everything. We have Thru coolant versions. We have, you know, all kinds of different various radii, things like that as standard. So let us know if you're doing any deep pocket or chatter applications with aluminum, and we could come up with a solution to help you. This is kind of a new solution for us. If you're doing like Swiss machining or just machining with slitting saws, a lot of people use ER collets, and what happens is it'll be a two-piece. You'll have the collet, and then you'll have the arbor, or you'll have the collet, and then you'll have the extension. And having multiple pieces just adds to the possibilities of having issues and run out and things like that. These are a one-piece design, so there's no slots in the collet. The collet isn't expanding and contracting. It's a solid piece there, and it really increases the rigidity and the run out. We're holding TI hard to 2/10,000ths of an inch with these types of extensions and arbors. And the huge advantage also is that you get repeated positioning. So you could loosen up the saw, put another saw in, and it's in the exact same spot. So really helps in medical applications, having this one piece ER integrated design, and we have them in various ER sizes and things like that for both slitting saws and end mill extensions, which are kind of common in the medical industry.
Well, here's the final poll for the presentation. Just a quick question. I need the most help using what? Slitting saws, end mills, drills. You can select one or more. So we'll give about 20 seconds for everyone to respond. Okay, I'm going to go ahead and close the poll. Thank you for participating in that. And again, we'll go over these after we're done with the presentation.
We're seeing things get smaller and smaller all the time. Most people aren't aware that people have all these sizes like on the shelf ready to ship. But here at RobbJack, we stock from 5/1000ths of an inch to 62/1000ths in every 1,000 increment. And I would say about at least 99% of the time I check, we always have them in stock. So we're stocking every one of them. Not to say that we wouldn't, one of them may not be in stock for a short period of time, but we really try to stock them all and have them same day shipping on those miniatures. And so in different configurations, 2 flutes, 4 flutes, different length of cuts, things like that. And here's a diamond coated miniature tool at 8/1000ths diameter, and you can see the size of the ant next to the tool. So we're able to make very, very small diameter tools. But the other thing people aren't aware of is because we have so many of the tools in stock, we can hand select to the nearest 2/10,000ths of an inch. So if you wanted an 8/1000ths and 4/10ths, we can probably find a tool that'll be 8/1000ths and 4/10ths for you. So we can hand select to the nearest 2/10,000ths of an inch, anywhere in between that 5/1000ths and 62/1000ths. Here's another, example, obviously not a medical part, but just to show how small the tool is. This is a dime, and that's a 3/1000ths diameter that we did a little logo on his ear. And then, here's an example of using a 15/1000ths diameter tool, and you can see all the intricate details, and things are just getting smaller and smaller in the medical field. Actually, in the majority of the fields, we're seeing things get smaller and smaller all the time. So our ability to grind these tools, tolerances, super tight tolerances, in the medical plastics, interocular lenses, things like that, take advantage of these types of tools. So one of the biggest challenges I hear out there is, how do I find the best tool to cut my specific material, or how do I get the speeds and feeds? So we have a speed and feed software button that's a dynamic tool search and a speed and feed that you can hook to your computer, or you can just go online and there's links to both of those programs. But it's super helpful and beneficial. And so what you're able to do is specify what kind of material you're cutting: aluminum, stainless, plastics, enter in, like what diameter you want, how many flutes, whether you're going to use coolant or not, all kinds of application information, and you only have to enter in what you want, and it'll tell you every tool that fits that criteria, depending on the different kinds of materials that you're cutting. And then on the right, you can see it's recommending the tools for that. And when you click on it, that tool, it'll give you all the specifications of diameter and tolerances, what it's used for, videos on how to use it. So it's very beneficial to find the best tool for your application. And if you wanted to send an email to me at the end, I would be glad to send these buttons out to you, these little program buttons that you can plug into your computer and get them, or you can go to our website as well and have access to it. The speeds and feeds, same thing. That button has two functions. If you click it, it gives you the speeds and feeds. If you hold it for a couple seconds, it'll take you to the tool search. But here's the speed and feed. Also, you could go to our website and just go to our speed and feed program. But once you create a user, you put your machine's properties, how much horsepower, what's the max RPM of your machine, what diameter tool. It's hard to see some of those entering, but it really doesn't matter. You know, depth of cut, trochoidal cutting, what type of material, you know, there's all different kinds of plastics, titaniums, different grades, 6AL4V, which is a common medical titanium. So it's saying you can go 73 inches per minute doing a trochoidal cut. What's the cost of the tool? All the tolerances, and you can save this and you can share it with people in your company. It's really good setup information because it gives you a really good starting point on how to use it. But you can see all the different kinds of materials, from aluminums to plastics to titanium and hardened materials and steels, and it'll recommend the tool as well as the speeds and feeds. And a lot of people are very, very complimentary to this because it really makes it way easier for them to get this sometimes very difficult material. It'll even tell you what the power, how much horsepower it's going to use, and all those types of things. So let me know if you want one of those buttons, or by sending me an email, and we'd be happy to follow up with you. So kind of to summarize, you know, when you use programming, cutting tool technology, and finding the right data, you put it all together, you can have tremendous gains in performance. And one thing I didn't talk about, but in the medical industry, we find very beneficial, is we have an in-house lab. So if you have some weird material or weird application, we can do in-house testing for you. We don't charge for that. You tell us what you're trying to achieve, and we'll test different tools and things to help you out of that difficult situation that you're in. So we'll go ahead. I'll leave this slide up for a while so you can, you know, have cell phone number, my email address. Most of the videos are right on our website. There's RJTV, but you could go there and it'll have all the videos there.
Okay, Mike, I can go over the, we've got a few questions, but I think first we'll just kind of share all the results from our polls, if that's okay.
Perfect.
So here's the first poll. What is your biggest pain when machining? The tool breakage is 6%, slow cycle times 28%, getting accurate speeds and feeds 25%, finding the best tool 19%, and poor finishes or poor part quality 22%.
All right. So it looks like you know, it's kind of pretty even for about 3 of them: slow cycle times, getting accurate speeds and feeds, and poor finishes. So the slow cycle times can be combated by getting application specific tools designed for your application, or you know, making sure that the tools that you're getting are made for that type of material that you're cutting. But a lot of it can be handled with just kind of what I tried. I had to go a little bit quickly on them, but those getting that tool recommendation as well as the speeds and feeds get you right in the ballpark. You'll get good finishes, you'll get accurate speeds and feeds, and it'll a lot of times increase or reduce your cycle time. So that getting that speed and feed data that we just showed should help with all three of those.
Okay, and our next one, most common material you are machining. Stainless steel is 44%, cobalt-chrome 3%, titanium 28%, PEEK or other plastics 3%, and aluminum 22%.
Wow, so I'm glad I included the aluminum. I was not going to include that, but it looks like the majority is the stainless steel. So for stainless steel, there's going to be various grades of stainless steel, but in general, stainless steel acts gummy, even though it could be hardened stainless steel. And so it usually, most stainless steels do benefit from using coolants because it acts gummy, even though it may be like in the hardened state. So using proper tools designed for that material, you know, using that high efficiency tool paths, that can really help increase performance and reduce cycle times, things like that, because instead of the slower 200 surface footage, you can be up in, you know, in the 300, 400, 500 surface footage range, depending on the stainless steel, and go much faster speeds and feeds by taking into account of not generating that heat. We talked about the aluminum. That's the biggest thing, is getting rid of the chatter. Titanium, very similar to the stainless, in it likes very light radial width, the cuts. Probably more problematic than the stainless is the titanium, in if you generate too much heat because it doesn't shed most of the heat away in the chip, you'll go downhill very, very quickly. More sensitive than the stainless steel is. And then we talked about the aluminum, getting rid of the chatter. Chatter is probably the biggest issue with aluminum. So by having that mirror edge can really help with that.
Good. And our final poll. I need the most help using splitting saws, 30%, end mills, 73%, drills, 35%.
So end mills, I expected, it seems like out in the industry, most people aren't as knowledgeable on the slitting saws, but there's a lot less applications with slitting saws, so that may be part of it. But on the end mill side of things, we went over, majority of most what we talked about was on the end mill side, and the slitting saw side, we talked a little bit about some of the problems. But that speed and feed software will help you get right into where you need, whether you're cutting with a slitting saw or you're cutting with an end mill. There's a button to switch between the two of them, and both of them will get you right in the ballpark of where you need to be on that using an end mill or saw. The other thing is really reach out to your cutting tool manufacturer, reach out to us at RobbJack. We have a team of guys that cut material every single day, that we have our in-house lab. Give us a call, send us an email, tell us, you know, the problems that you're having, and more than likely we've already experienced what you're running into. So we'll have a you know, a solution for you to dial in those tools very quickly.
We've got a few questions that I hope we can squeeze in here. Somebody asked if it's regarding sawing, wants to know if there's some of the drawbacks or benefits and differences in HS slitting saws versus carbide slitting saws. because this person's had some difficulty in some of his operations.
Yeah, so that's an excellent question. And in general, and every application may be different. So a high-speed steel saw may be better suited than the carbide, but in general, usually carbide is a little bit better suited, unless it was a high-speed steel is a little tougher than the carbide in its ability to resist chipping. So if you had a very weak machine and everything's loose and you had a arbor that was not a very tight tolerance, things like that, the high-speed steel saw may be better suited. But as far as speeds and feeds and wear and ability to get pretty amazing geometries, the carbide is going to be the better choice in most of the time. And we're, like I said, we're able to put all these new geometries on the saws and use the through coolant and things like that. So I would say the majority of the time carbide will outperform high-speed steel, except if you had a very weak old machine, not accurate. With the carbide, you do need to have very, very accurate arbors, tool holders. You need to indicate the saws in. And on that RobbJack TV link that we have at the bottom of the screen, that has an excellent video on how to indicate the saws in, what those numbers need to be, what's the max run out. If you do run into run out, how to fix it, how to clean the saws, how to assemble them. And it's only like a 2-minute video or 2.5-minute video. Every person that uses a slitting saw should watch that because it could reap huge benefits.
Okay, Mike, we are coming up to the end of the webinar, but I'm going to try to get these other questions in. Do you recommend climb milling when you edge cut?
I would say we recommend climb milling about 95-98% of the time. There are some materials, like if the material is flexible and like not rigid, sometimes conventional milling will help pinch the material into itself, like rubbers and you know, maybe like an interocular lens that's you know, it's like Jello. You know, sometimes conventional milling will help pinch the material into itself, which if it's flexible and a very soft, pliable material, can be beneficial. But 95 to 98% of the time, climb milling will give you better finishes, better accuracies. It's better on the tool. So majority of the time, climb milling.
Okay. Also, what kind of measurement equipment do you use or suggest for the tight tolerance tools?
So internally, we use equipment that most people wouldn't have. Like internally, we use jeweled air gauges that can measure to millionths of an inch. We use lasers. We use super high-end vision systems that compensate for any kind of run out in a holder and things like that. But in general, like on the end user side, you want to use non-contact measurements, whether you're using PCD or carbide. You really don't want to mic the tool or use calipers, or you really want microscopes or vision systems. All of those non-contact measurements will not chip the tools, and a lot of medical applications are very sensitive to having any kind of chip or mark on there. So you really don't want to use the micrometer or if you're measuring a shank or something like that on non-cutting edges, it's fine to use micrometers or calipers, things like that. But you never want to do that on cutting edges.
Okay, we are just a little bit over our allotted time. Is there anything that you'd like to add, Mike, before we close out?
No, I'm good. If you guys submit your questions and we didn't get to it or anything like that, we'll answer all the emails or send me an email, and we're here to help. So let me know if there's anything we can do to make it easier and take away some of those machining pains. Thank you very much for spending this time with us. We appreciate it.